Agni, the fire, is the most potent source of light and heat energy. Since hundreds of millennium, fire has significantly contributed to the progress of humankind on the path towards civilization. It has banished darkness and provided knowledge, helped shape things of daily use, and aided societies to keep on the move. How did fire come into being? And how did man learn to use it? There are no definite answers to these questions. Blazes ignited by volcanic conflagration and lightning are speculated to have served as man's first source of fire. From such terrifying blazes, primitive man is believed to have kindled his own fire over 5 lakh years ago and gradually become conversant in using it for various purposes, such as to keep himself warm, to hunt animals, and to cook food. Much later, in the Neolithic age, he used fire to clear forests for agriculture and human settlements, and also learned to make fire by striking flints together, or by using simple tools such as the fire saw, the fire plow, and the fire drill. Since then, the application of fire has brought about significant changes in man's ways of living. In particular, it was the application of fire in pottery, in extraction of metals, and in their conversion into alloys that led to the emergence of the Metal Ages. For the growth of civilizations in ancient Greece, Egypt, and the Indus Valley, and of course, for the industrial revolutions of the last few centuries, fire has immensely contributed. But fire, which has benevolent and destructive powers, was a mystery to the ancient people. They believed it to be of heavenly origin. According to Greek mythology, fire was stolen by Prometheus for the good of his fellow beings. The Persians interpreted fire as a true gift of the gods, fit to be venerated and worshipped. The Vedic societies looked upon Agni the fire as a divine being who resides everywhere, despising none. He is the possessor of power and wealth, and the divine messenger between the god and human beings. As did the Vedic mystics, the Greek philosophers, Plato and Aristotle, thought fire to be an element essential for the constitution of life and matter. Such mystical ideas prevailed until the later 18th century, by which time scientists had discovered the essentiality of air for the occurrence and persistence of fire. Antoine Lavoisier, in 1772, showed that an active fraction of air combines with burning substances, making them weigh more than they initially did. Fire, he explained, is a result of a chemical reaction between oxygen and flammable substances.
The complex phenomenon of fire is basically a manifestation of combustion. Combustion can be defined as an extremely rapid chemical reaction in which a combustible substance combines with oxygen from the air, producing combustion products along with the emission of heat and light in the form of flame.
Not all combustions, however, result in fire. Often, oxygen unites with some substances at such a slow rate that little heat or no light are given off. Such a slow reaction is called a slow combustion rather than burning, which is very rapid. A good example is the rusting of iron.
Before we go into the details of chemical reactions involving flammable vapors and oxygen that yield fire, let us look at the conditions needed for fire to occur.
First, there should be a fuel. Most fuels are complex hydrocarbon compounds. A fuel could be a solid such as coal or wood, a liquid such as oils, and a gas such as methane. Second, there must be plenty of oxygen. Third, the fuels must be heated to ignition temperature, at which they undergo thermal decomposition, releasing flammable vapors with which oxygen unites rapidly in a chemical reaction. In fact, all fuels, except gases, must first be converted to their gaseous state for them to yield fire. It is therefore that kerosene, a liquid fuel, though exposed to air, will not catch fire even when a pilot flame is brought in contact with it. However, upon heating directly to its ignition temperature, kerosene converts into its vaporous state. Now, when a burning stick is brought close to the vapors, they combust readily into a flame. In the case of combustible solids, heat decomposes involatile fuel molecules into tiny volatile molecular fragments which react with oxygen of the air to yield fire, producing a series of combustion products.
Let us investigate chemical reactions by taking the example of methane and oxygen.
Each molecule of oxygen contains two oxygen atoms which are bonded together. Methane is a natural gas. Each of its molecule contains one carbon and four hydrogen atoms bonded together in a particular arrangement by a force arising from electron sharing, which accounts for the molecular energy. When methane is ignited, the bonds break, freeing carbon and hydrogen atoms, which then react separately with oxygen. One carbon and one oxygen atom unite to form carbon monoxide. One oxygen and one hydrogen atom combine to form the hydroxyl radical. While carbon monoxide combines with one oxygen atom to form carbon dioxide, the hydroxyl radical unites with one hydrogen atom to form water. These products of combustion then escape into the atmosphere.
The total energy of combustion products tends to be less than those of the fuel and oxygen involved in combustion. The difference in energy gets released as the heat of the fire. It is therefore that combustion reactions producing fire are exothermic chemical reactions.
Let us now take the case of wood, a solid fuel, the bulk of which is cellulose and water. Lignin, resins, and inorganic substances form the rest of the woody matter.
Wood, which produces upon burning carbon dioxide and water, contains cellulose, which is a polymer of glucose units. Each unit contains 6 carbon, 10 hydrogen, and 5 oxygen atoms. Wood upon burning also yields charcoal and ash, which are a mixture of unburnt carbon particles and inorganic substances. In the fire, where do these extremely complex chemical reactions occur, producing a series of combustion products.
The complex reactions between fuel and oxygen occur in the flame zone. A flame is recognized as a glowing body of oxygen and fuel in their vaporous or gaseous state, undergoing the process of combustion, producing heat and light.
In some burning systems, the combustion of fuels tend to be incomplete due to insufficient supply of oxygen. This results in a luminous yellow flame as that of a matchstick.
Some fuels can undergo complete combustion when there is sufficient supply of oxygen for the fuel to burn completely. Such burning systems produce a blue flame. The flame of the Bunsen burner is a good example.
Based on this difference, flames are usually classified as either diffusion flames or premixed flames. Diffusion flames are those flames in which oxygen needed for combustion diffuses from the surrounding air and therefore meets the fuel only at the flame.
Let us learn more about diffusion flames by examining the flame of a candle.
When a candle is lit, the heat of the matchstick melts the wax, which is a hydrocarbon compound. The molten wax is carried up the wick and vaporized. The vapors finally burn in a diffusion flame containing 4 distinct zones. Around the wick is the dark non-luminous region containing volatile unburnt wax vapors. Hugging the dark zone is a yellow brightly luminous zone where decomposition of hydrocarbon molecules takes place. Some of the hydrogen and carbon monoxide produced by decomposition react with available oxygen to form water and carbon dioxide respectively in this zone. The free carbon particles produced in this zone are responsible for the diffusion flame's yellow luminance and sooty nature. Soot is nothing but unburnt carbon particles. Outside the luminous zone is the third faintly visible non-luminous zone, where some of the carbon monoxide, carbon and hydrogen undergo a final phase of reaction with oxygen of the air. Lastly, there is a 4th blue zone at the base of the flame. Here, some of the carbon monoxide formed in the luminous zone undergoes complete combustion by reacting with plentiful oxygen to form carbon dioxide.
Let us now examine the case of premixed flames, which result from those burning systems where fuels are mixed with oxygen prior to their entry into the flame zone.
The flame of the Bunsen burner is a good example of a premixed flame. Named after Robert Wilhelm Bunsen, a German scientist, the burner consists of a metal barrel into which gaseous fuel is injected under pressure through a nozzle. To provide appropriate quantity of oxygen needed to burn the gaseous fuel completely, the barrel is equipped with air holes, through which air gets sucked into the barrel where it mixes with the gaseous fuel. On ignition, this fuel-oxygen mixture burns with a hot, soot-free, predominantly blue flame having 3 distinct zones. The inner zone, close to the mouth of the burner, is dark because it has cold, unburnt mixture of gaseous fuel and oxygen. Therefore, a stick placed in this zone readily burns on the 2 sides touching the blue flame, while the central portion in the dark zone remains unburnt. The dark region is capped by a narrow, bright bluish-green mantle, a zone of chemical reaction. Here, the hydrocarbon molecules break into free hydrogen and carbon. These react quickly and rapidly with a premixed, abundantly available oxygen to form carbon dioxide and unstable carbon monoxide and hydroxyl radicals. The unstable products undergo further reaction in the outermost pale bluish and turbulent flame zone, yielding carbon dioxide and water vapor. As all the fuel gets consumed without any loss, These carbon-free, non-sooty and non-luminous flames produce a high temperature. Therefore, premixed flame systems have several industrial and domestic applications. One such example is a domestic gas stove into which a fuel, that is, liquefied petroleum gas, is fed through a pipe underneath the stove. On the pipes are air ports through which air enters and oxygen present in it mixes with the fuel, which emerges from the tiny holes of the burner. On ignition, the mixture burns in a soot-free blue flame with a temperature of over 1000 degrees centigrade. Still hotter flames, required for special purposes in industries, are obtained by burning gaseous fuels such as acetylene mixed with oxygen under pressure. The oxyacetylene mixture, when burnt, gives out a premixed flame with a high temperature of over 2300 degrees centigrade. The mystery that is Agni, the fire, is no longer an unsolved phenomenon. Quite simply, it is a physical manifestation of combustion that helps man harness the bounties of the earth as well as those of the heavens. With thousands of everyday uses, turning the proverbial darkness of human existence into a celebration of light.